In this video we look at pulleys and Newton's laws. Example 2. These two masses are connected by this light inextensible string, and they both go over this pulley, which is smooth. So there's no friction on the pulley. The tension in the string here and here is the same. There is friction between block A and the surface. When this system is released, so initially everything is at rest, when the system is released, B will accelerate towards the ground. Because the string is tight, block A and B experience the same acceleration, the same magnitude of acceleration. For problem solving, we split the system in half, so we look at block A and B separately, which greatly simplifies things. So in terms of forces, we have a downward force here because of the weight of B. There will be a tension in the string there. There will be a tension in the string here. There will be a normal reaction force here. There will be the force due to the weight of block A. There will be a frictional force opposing motion for block A. So let's start by looking at block A. Okay, so this is the information that's already given in this problem. So we're looking at forces in the horizontal direction, and I'm taking this direction as positive. There is acceleration present horizontally, so Newton's second law, F equals ma. So the resultant force will be T minus 0.08 g equals the mass 0.4 kilograms times the acceleration. So this is the resultant force, this left hand side, when we're looking at resolving forces horizontally. Vertically there is no acceleration, so from Newton's first law the upward and downward forces will be balanced, so R is equal to 0.4 g. Now looking at block B, we have an acceleration that's downwards, so if we take the downwards direction as positive and apply Newton's second law, so F equals ma, so 0.8 g minus T will give you the resultant force. The mass is 0.8 kilograms times A, the acceleration. So we have a second equation now. So to work out the acceleration of the system, if we solve both equations simultaneously, the acceleration in its exact form is 0.6 g, or 5.88 meters per second squared. And we're assuming that g is 9.8 meters per second squared. Now we can see that the acceleration is a constant. It's not a function of time. So we can use Suvat formulae for problem solving. So the time for B to reach the ground, so it's 0.5 meters above the ground. Initial velocity is 0, it's stationary initially, the whole system is. We're not interested in the final velocity. The acceleration we have already here, and we need the value of t, how long does it take. So finding an appropriate Suvat formula, substituting the values in, the initial value for u there is 0, so 0 times t is 0, so there's no term there for this part of the formula. And remember to square root at the end, that's t squared, and it's 0.41 seconds to two significant figures. Now this diagram is not drawn to scale. You can see that the height of B above the ground is 0.5 meters, and that there on the diagram is 4 meters, so that's significantly more in reality than this distance here is. So as the system accelerates and B is going towards the ground, as soon as B hits the ground, the tension in the string is no longer what it was before. The string becomes slack, and then A is moving with a certain velocity at that point. As soon as B hits the ground, A is moving with a certain velocity, and B is no longer pulling on A through that string, but there is this frictional force that will eventually bring A to a stop. So either A makes it all the way to the pulley and hits the pulley and then stops, or A will stop before it hits this pulley. So we can represent this on a velocity time graph for A. So here's velocity, and initially block A is at rest, and then we know there was constant acceleration, so we need a straight line graph in this region until we get to a point where B hits the ground, and then the string becomes slack, so there's no tension in the string anymore, it's no longer pulling on A, and then A will experience a constant deceleration, and we can see that the graph here has a negative gradient, and the deceleration will be due to this force, the frictional force, 0.08 times G. So after B hits the ground, the only force acting on A now horizontally is the frictional force. Now we have taken the right hand direction as positive because the block is moving towards the right, so I've taken that as positive, but the force here is in the opposite direction, so I need to be careful with my signs when I write down F equals ma. So the resultant force is negative equals the mass times the acceleration. Now A will turn out to be negative because the block is slowing down, and we can call it deceleration. The acceleration is minus 0.2 g. That negative tells you it's in the opposite direction to the arrow, so it's slowing down. Or another way of saying this is the deceleration is 0.2 g meters per second squared. Yeah, when I said deceleration, I didn't mention the minus with it. Yeah, the word minus and deceleration are equivalent. So using some Suvat's formulae, the velocity reached by A at this point where B hits the ground will be exactly the same as the velocity of B before it hits the ground. Yeah, they were connected by the string at that point, and the string was tight. So V equals U plus AT. Initially the system was at rest, so U is 0. A is equal to 5.88 meters per second squared. We worked that out before, and this is the exact value of T, 5 root 3 over 21. So this is the exact value of the velocity, meters per second, when the string becomes slack, when B hits the ground. So then we've got V squared equals U squared plus 2AS. The final velocity when A comes to a rest is 0. Its initial velocity, and that's where B hit the ground, is this. We just worked it out here. It's now here, squared, U squared, plus 2. The acceleration was minus from there, look, minus 0.2 g, and times s, which is what we're after. So we rearrange, and we've got s equals 1.5 meters. So initially A was at rest, and it experiences constant acceleration up until the point where B hits the ground, and in this portion of its journey it's traveled 0.5 meters. Yeah, that's got nothing to do with the time axis here, they're separate. And then we have the second portion of its journey where it's decelerating, and to work out the distance traveled during its deceleration phase, I've done that here, so that's 1.5 meters. So that's where that 1.5 comes from, and that's where that 0.5 meters comes from. So a total distance of 2 meters traveled. For practice, try these questions.